Welcome to today's session. In this video, we'll explore the problem number 978, longest turbulent subarray. This is an exciting challenge where we'll dive into arrays and identify the longest subarray that exhibits turbulent patterns. Let's get started. In this problem, we are tasked with finding the length of the longest turbulent subarray within a given integer array, ARR. A subarray is considered turbulent if the comparison between its adjacent elements alternates strictly. For instance, a subarray is turbulent if, for every valid pair of adjacent elements, one element is greater than the next, and the following element is smaller than the one after it, or vice versa. However, if the subarray contains fewer than two elements, it cannot be turbulent. The input is an integer array ARR, where the length of the array can range from 1 to 10,000, and each element can have a value between 0 and 1 billion. The output is a single integer representing the length of the longest turbulent subarray in the input array. For example, consider the input array 9, 4, 2, 10, 7, 8, 8, 1, 9. The output for this input is 5 because the subarray 4, 2, 10, 7, 8 satisfies the turbulent condition. Specifically, 4 is greater than 2, 2 is less than 10, 10 is greater than 7, and 7 is less than 8. This alternating pattern of comparison signs makes the subarray turbulent. No longer turbulent subarray exists within the array, so the result is 5. Now, let's look at another example. If the input array is 4, 8, 12, 16, the output is 2. Here, no subarray longer than length 2 alternates strictly in its comparison signs. For instance, the subarrays 4, 8, 8, 12, and 12, 16 are all turbulent because they meet the criteria for alternating comparisons, but none of them can be extended to include additional elements while maintaining turbulence. Therefore, the maximum length is 2. Finally, consider the input array 100. In this case, since the array only contains a single element, there are no adjacent elements to compare, so a turbulent subarray cannot exist. By definition, however, the longest subarray in this scenario has a length of 1. Additionally, as we approach the problem, it's critical to consider edge cases like arrays with all equal elements or arrays with minimal lengths, ensuring that we handle these scenarios correctly when determining the maximum length of a turbulent subarray. To tackle the problem of finding the longest turbulent subarray, we first consider a brute force approach. The intuition here is straightforward. We examine every possible subarray of the given array and check whether each satisfies the turbulent condition. Specifically, we verify if for every I in the subarray, the sequence alternates between ARR, I1, RR, I plus 1, or RR, I1, RR, I plus 1. While this approach is conceptually simple, it involves generating all subarrays, which takes O, n squared, and then validating each subarray, which can take O the n, in the worst case. This results in an overall time complexity of O, n cubed, or O, n squared, if we optimize slightly. However, such a method is computationally expensive and impractical for larger input sizes, especially given the constraints where the array can have up to 10,000 elements. Recognizing this inefficiency, we turn to a more optimized approach leveraging the sliding window technique. The key observation for this is that we don't need to generate subarrays explicitly. Instead, we can focus on maintaining the alternating pattern of comparisons as we traverse the array. Using the sliding window approach, we define two pointers: start, which marks the beginning of the current turbulent window, and end, which expands as we iterate through the array. For each position of end, we check whether the turbulent condition holds. Specifically, we determine if the sequence satisfies either ARR n1, ARR end, ARR n plus 1, or ARR n1, ARR end, ARR n plus 1. If the condition is met, we extend the window by moving in forward. If the condition is violated, we reset the window by setting start equal to end. Throughout this process, we track the maximum length of any valid turbulent window encountered. This method is highly efficient, as each element in the array is processed only once, leading to a time complexity of O, n. There are a few key observations here. First, the alternating pattern relies on comparisons between elements, not their exact values, making the approach generalizable. Second, resetting the window ensures we focus only on valid turbulent sections without redundant checks. While this approach is efficient, edge cases like consecutive equal elements require careful handling, as they can interrupt the turbulent pattern. After evaluating the options, we chose the sliding window approach for its balance of simplicity and efficiency. Unlike the brute force method, which redundantly generates and checks subarrays, the sliding window dynamically adjusts to include only valid turbulent sections. This makes it optimal for the problem's constraints, as its linear time complexity of O(n) ensures it scales well with larger input sizes. Additionally, the space complexity remains O(1), as we only use a few pointers and counters to track the window and its properties. Beyond efficiency, the sliding window approach is also relatively easy to implement, reducing the likelihood of errors compared to alternatives like dynamic programming, which could introduce unnecessary complexity for this problem. Overall, this strategy provides the right balance of performance, clarity, and practicality, making it the most suitable choice to solve the problem effectively. In this problem, the goal is to find the length of the longest turbulent subarray within a given array. A subarray is considered turbulent when its elements alternately satisfy the conditions of being greater than and less than their neighbors. Specifically, at any index I, the subarray must satisfy either AR, I1, I plus 1, or R, I1, I plus 1, for all valid indices. To solve this efficiently, we'll use a sliding window approach. This method allows us to traverse the array in a single pass, dynamically adjusting the size of the window based on whether the turbulent condition holds. First, we initialize two pointers, start and end, both set to 0. These pointers define the bounds of the current subarray. Additionally, we maintain a variable max_len that tracks the maximum length of a turbulent subarray found so far. We initialize max_len to 1, as the minimum length of any subarray is 1, corresponding to a single element. To implement the sliding window approach, we traverse the array using the end pointer, starting from the second element. For every position of end, we check whether the turbulent condition is satisfied for the subarray ending at end. Specifically, if n is greater than or equal to 2, we examine whether the three elements AR, N2, AR, N1, AR, end satisfy either AR, N2, AR, N1, AR, end, or AR, N2, AR, N1, AR, end. If the condition holds, we expand the window by moving the end pointer forward, update the length of the current turbulent subarray as end start plus 1, and compare it to max_len, updating max_len if the current length is larger. If the turbulent condition fails, we reset the window by moving the start pointer to the current position of end and continue the traversal. It's also important to handle edge cases, such as when the array has fewer than 2 elements, in which case the length of the turbulent subarray is simply the array's length, or when all elements are identical, or the maximum turbulent subarray length is 1. This approach leverages the sliding window technique to achieve efficiency. By dynamically expanding and contracting the window, we avoid the need to generate all possible subarrays, which would have a time complexity of O(n squared) in a brute force approach. Instead, the sliding window approach ensures a linear time complexity of O(n), as each element is processed at most twice, once when expanding the window and once when contracting it. The turbulent condition itself is checked in constant time, as it involves only a comparison of 3 elements. To ensure robustness, we must carefully handle edge cases, such as small arrays or arrays with uniform elements that lack turbulence. The data structures supporting this algorithm are minimal: 2 pointers, start and end, to define the current subarray bounds, and a variable max_len to track the longest turbulent subarray length encountered so far. With these optimizations, the space complexity is O(1), since no additional data structures are used beyond a few variables. To understand this process better, consider the example array ARR equals 9, 4, 2, 10, 7, 8, 8, 1, 9. Initially, we start with start equals 0, end equals 0, and max_len equals 1. As we expand the end pointer, we check the turbulence condition at each step. For instance, at end equals 2, the subarray 9, 4, 2 is not turbulent, so we reset start to 2. Then, at end equals 4, the subarray 2, 10, 7 satisfies the turbulent condition, and we update max_len to 3. Continuing this process, we eventually find that the longest turbulent subarray is 10, 7, 8, 8, 1 with a length of 5. To further optimize, we can terminate the traversal early if the remaining elements are fewer than the current max_len, and we can track the last comparison direction to simplify the turbulent condition checks. This method provides an efficient and clear solution to the problem, ensuring that we achieve optimal performance while handling various edge cases effectively. This solution uses a sliding window approach to efficiently compute the longest turbulent subarray in the given array ARR. The algorithm iterates through the array while maintaining the starting index of the current turbulent subarray. As it progresses, it checks for the turbulent conditions, ARR, I1, ARR, I plus 1, or ARR, I1, ARR, I plus 1. If the turbulent pattern breaks or two consecutive elements are equal, the current window is adjusted, and the maximum length is updated accordingly. The result is the maximum recorded length of any turbulent subarray during the traversal. This approach ensures an O(n) time complexity, where n is the length of the array, and it handles edge cases like arrays with a single element or arrays containing repeated values effectively. This is the Java implementation of the longest turbulent subarray problem. It mirrors the logic from the Python solution, with adjustments for Java syntax and type declarations. Key points include using math.max for comparisons and handling array bounds carefully. The solution efficiently identifies turbulent subarrays in O(n) time complexity. To solve this problem, we start by initializing a few variables, n as the length of the input array, which is 9 in this case, max_len to track the length of the longest turbulent subarray, and start to mark the beginning of the current window. As we iterate through the array starting from index 1, we compare consecutive elements. When I equals 1, we compare ARR 0 and ARR 194, which satisfies a turbulent condition, so we continue. At I equals 2, ARR 1 is greater than ARR 2 for 2, but the turbulent pattern breaks because two consecutive comparisons are in the same direction. Here, we calculate the length of the window, which is 2 0 plus 1 equals 3, and update max_len to 3. Then, we adjust start to 2 to begin tracking a new window. Moving to I equals 3, the comparison ARR 2, ARR 3, 210, re-establishes a turbulent condition, so we continue. This continues through I equals 4 and I equals 5 with alternating conditions, but at I equals 6, the pattern breaks because RR 5 equals RR 6. We reset start to 6. Finally, the pattern alternates again for indices 7 and 8, and we calculate the maximum length of the turbulent window as 4. The final output here is max_len equals 4. In this example, the input array is 4, 8, 12, 16. We initialize the same variables as before, with n equals 4, max_len equals 1, and start equals 0. Starting the iteration at I equals 1, we compare ARR 0 and ARR 1, for 8 satisfies a turbulent condition, so we continue. At I equals 2, however, ARR 1, ARR 2, 8, 12, which breaks the alternating pattern because both comparisons are in the same direction. We calculate the length of the current window as 2 0 plus 1 equals 2 and update max_len to 2. We set start to 2 to begin a new window. At I equals 3, the comparison ARR 2, ARR 3, 12, 16 again breaks the turbulent condition, so we calculate the window length as 3, 2 plus 1 equals 2. Since max_len is already 2, it remains unchanged. The final output for this example is max_len equals 2. Here, the input array consists of a single element, 100. After initializing n equals 1, max_len equals 1, and start equals 0, we immediately return max_len equals 1 because there are no other elements to compare, and a single element is trivially a turbulent subarray of length 1. This concludes the example. From these observations, we can summarize the key insights of the algorithm: the use of a sliding window from start to I to track turbulent subarrays, the termination of the window when the turbulent condition breaks, and the immediate reset of the window when equal adjacent elements are encountered. With a single pass through the array, the algorithm achieves an efficient O(n) time complexity. In this algorithm, we process the input array using a sliding window approach, which ensures that we traverse the array just once. Now, let's break down the time complexity. First, we initialize variables such as n, max_len, and start. These operations are straightforward and happen in constant time, so they contribute O(1) to the overall complexity. Next, the main work happens inside the loop, which iterates from index 1 to n1, meaning it runs n1 times. Within each iteration, we perform a few key operations. Condition checks, like determining if the current subarray is turbulent or if two consecutive elements are equal, are simple comparisons and take constant time per iteration. Similarly, updating the max_len variable or resetting the start pointer also involves constant time operations. Since the loop executes a constant amount of work in each of its n1 iterations, the total contribution of the loop to the time complexity is linear, or O(n). Finally, at the end of the algorithm, the return statement simply outputs the value of max_len, which is a constant time operation and contributes O(1) to the total complexity. When we sum up all these components, the dominant term comes from the loop, which processes the array in O(n) time. Therefore, the overall time complexity of the algorithm is O(n). Now, in terms of space complexity, the input array ARR is not modified or duplicated, and the algorithm does not allocate extra memory for additional data structures. The space used by the input itself is O(n). Beyond that, we only use a fixed number of auxiliary variables, including n, max_len, start, and the loop index I. These variables require constant space, or O(1). Since no additional memory is allocated, the overall space complexity of the algorithm is O(1). When we analyze the algorithm under different scenarios, the complexity remains consistent. In the best-case scenario, the array alternates perfectly between increasing and decreasing values, creating a fully turbulent subarray. Even in this case, the loop iterates through all the elements, so the time complexity remains O(n), and the space complexity stays O(1). For the average case, where the array has a mix of turbulent and non-turbulent segments, the loop still processes all elements linearly, resulting in the same time complexity of O(n) and space complexity of O(1). In the worst case, where the array has no turbulence at all, such as when all elements are equal, the loop still iterates through the entire array, yielding the same time complexity of O(n) and space complexity of O(1). Across all scenarios, the algorithm's efficiency is maintained. To understand why the sliding window approach is so efficient, let's compare it to a brute force method. A naive solution would involve generating all possible subarrays, checking each one for turbulence, and then determining the maximum length. Generating all subarrays of an array takes O(n)² time, and checking each subarray for turbulence can take O(n) in the worst case, leading to a total time complexity of O(n)³. Additionally, the brute force approach may require O(n) space to store each subarray. In contrast, the optimized sliding window approach avoids generating subarrays entirely. It processes each element just once and maintains a single window for computation, reducing the time complexity to O(n). Furthermore, it efficiently tracks turbulence without requiring extra memory, resulting in a space complexity of O(1). By iterating through the array linearly and using only constant space, this solution achieves significant improvements in both time and space efficiency. When solving the longest turbulent subarray problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to incorrect results. For instance, if the array contains only one element or all the elements are identical, the maximum turbulent subarray length is simply 1. Assuming the array always has a mix of increasing and decreasing elements can cause your solution to fail in these scenarios. Another mistake is using non-strict inequalities like greater than or equal to or less than or equal to when comparing adjacent elements. Turbulence requires strict alternation between increasing and decreasing comparisons, so these relaxed inequalities can lead to identifying incorrect subarrays as turbulent. Lastly, it's easy to overcomplicate the sliding window approach by introducing too many variables or not properly resetting window boundaries. This can create unnecessary complexity and lead to subtle bugs when handling new turbulent subarrays. Another issue to be mindful of is time complexity. A brute force approach that checks all possible subarrays runs in O(n)² time, which becomes impractical for larger arrays, such as those with 10,000 elements. Optimized methods, like the sliding window technique or dynamic programming, allow for an O(n) solution, which is much more efficient and avoids timing out. Additionally, ignoring array boundaries during comparisons can cause runtime errors. For example, when comparing elements at indices I1, I, and I+1, accessing out-of-bound indices such as when I is the first or last element can lead to crashes. Always ensure your solution includes boundary checks to handle these situations gracefully. When discussing this problem in interviews, there are a few key points to emphasize. Recognizing patterns is crucial, specifically, the alternating relationship between elements in turbulent subarrays. Clearly explain this pattern to demonstrate your understanding. It's also important to discuss trade-offs, for example, why an O(n) solution is superior to O(n) squared, and how techniques like sliding window or dynamic programming optimize performance. Showing awareness of edge cases, such as arrays with only one element, all equal elements, or very large arrays, highlights your attention to detail. Additionally, interviewers value incremental problem solving. Start with a brute force approach to show your intuition and understanding of the problem, then refine it to an optimized solution to showcase your ability to improve efficiency. For further practice, focusing on related problems can help reinforce these skills. Some related problems to this one include LeetCode 53, Maximum Subarray. This problem helps you practice identifying subarray patterns and applying optimization techniques like sliding window or dynamic programming. Another is LeetCode 845, Longest Mountain in Array, which involves recognizing sequences that first increase and then decrease, making it conceptually similar to turbulent subarrays. Lastly, LeetCode 376, Wiggle Subsequence, focuses on alternating increases and decreases, presenting another opportunity to work on problems with similar alternating patterns. Solving these related problems can deepen your understanding of the underlying concepts and prepare you for variations in interviews. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force method, with O(n) squared complexity, involves checking all possible subarrays to determine if they are turbulent. While simple to implement, it becomes inefficient for larger arrays. A more efficient solution is the sliding window approach, which operates in O(n) time. By maintaining two pointers to define the boundaries of the current turbulent subarray, this method optimizes performance but requires careful handling of window updates to ensure correctness. Another O(n) solution is dynamic programming, which uses variables or arrays to track the maximum turbulent subarray length at each index. While it shares similar efficiency with the sliding window technique, dynamic programming may require additional space depending on the implementation. Understanding these approaches and their trade-offs can help you choose the best solution for different scenarios. Great job! We've successfully tackled the longest turbulent subarray problem. Remember to apply concepts like sliding windows and efficient array traversal to similar challenges. If you enjoyed this, please like, share, and subscribe. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!